Welcome back to Lab 5 of the Bayesian Machine Learning module of the FMML course. In this lab, we are going to see the culmination of methods that we have learned across the module, and we are going to apply it to model some complicated phenomena. Till now, we have used Bayesian methods only for a single stage learning process, which is we have used it for a single stage clustering or a single stage classification task. However, we have not modeled a chain of tasks that are dependent on each other, and we understand the latent structures of these tasks, that is, which task depends on what, but we can only observe the final output occurring as a result of these tasks. So let's take a look at one example. The example that we are going to work with throughout this course, throughout this lab, is one of a user who is sending and receiving text messages. We have a daily message count of how many messages he sends or receives. Now we know that this is a piece of noisy data, meaning that there is no correct value and the estimates are going to hover over and below a certain threshold. However, we have some notion that the user might have started texting a little more or a little less during some sub window, or the number of texts may have increased at a certain point in time. We want to figure out what position, what are the days which show this increased activity. Intuitively, by just going by the human eye, it's sort of hard to figure this out. Where does the pattern of behavior change? There are some huge spikes in the middle over here, but it's not clear that it's consistently spread along the entire window. And we are given the fact that there is an increase or decrease because of some event, like if there are exams happening, maybe the person will start texting his friends more as they prepare together and stay at home. So given this sort of data as the input, where x is the date index and y is the number of text messages sent on that date, we want to come up with a probabilistic model. And here we start with some intuition that we have on different types of random variables and different types of distributions. The number of text messages that each person receives every day should sort of be sampled from a Poisson distribution. The reason for doing this is that, first of all, Poisson has a integer valued support, which is exactly what we want, and it resembles a bell curve but is skewed towards a longer tail because you can get infinite text messages or a very high number of text messages with very low probability, but you can get 0 text messages, you can get no less than 0, and you would have some peak at a value like 3 or 4 or somewhere in the middle over here. So we have plotted a bunch of different Poisson distributions, and the probability of receiving, say, 7 messages is proportional to the height of the histogram over here on any random given day, and this sort of makes sense. Assuming that the probability of receiving 5 messages is the highest, probability of 7 is lower, 8 is yet lower, and so on. It falls off in both directions, falling off rather steeply towards 0. Next, the Poisson distribution, we know, takes some parameter lambda, and we believe that this parameter lambda is going to be affected by whether or not there is an exam or there are other events going on in your life. The value of lambda would change such that the number of messages become more when the exam is going on, and the number of messages become less otherwise. So this lambda is what is expected to change. And Ci was the observed variable that we have. We have supervision on the values of Ci, and lambda is a latent parameter. It is not one of the inputs of the model, but it is one of the parameters that we are trying to learn as a outcome of other ground truth parameters. So now let's try to figure out what this lambda will be. And what we can say is that this lambda will be either lambda 1 or lambda 2, switching at some point t. Such a model is called a Bayesian Switchpoint model because we are trying to find out that position at which the value of the lambda changes. And lambda 1 is representative of how much the person texts on a normal day, for example, or just in the first half of the window, and lambda 2 is representative of how much he or she texts on the second half of the window. If there was an exam, we'd presume that lambda 2 would be higher than lambda 1, assuming that the exam comes later down the window. Further, we do not have exact values of lambda 1 and lambda 2 because these are again random variables corresponding to a person's behavior. Every single person may have a different rate of number of messages they send on a normal day and on an exam day. I might send 5 or 10 text messages every day, whereas one of my friends may be sending 100 text messages on a random day. However, we know that over all the different humans on Earth, there exists some distribution of the number of text messages they send on a normal day. So what we can say is that these lambda 1s and lambda 2s are also sampled from some exponential distribution. This exponential distribution is parameterized with alpha, and this exp of alpha represents the distribution of the number of messages that people send in general, averaged over all of the people on Earth. Now note that alpha, the exponential distribution of alpha controls this lambda parameter, and the lambda parameter controls the Poisson random variables. Let's take a look at how the Poisson variables are affected when we change lambda. So in this example, we have gone through values of lambda from 1 to 10, and we have sampled it at 9 different locations. And as you can see that as we increase the value of lambda, the number of text messages a person receives on average keeps on increasing. So the higher the lambda, the more number of messages you get, and the longer off your tail becomes. So in our example, whenever we have this exponential distribution, these people, the people who are represented by these histograms on the left, on average receive fewer text messages, and the people who are on the histogram on the right, on average receive more text messages. However, it's not that a single person on the left always receives few text messages. A single person who is here on the left has a text message profile modeled by this first chart over here, where he can receive more text messages but with very low probability. Alright, so here we have modeled the different type of people, and over here at the top we have modeled the number of text messages they receive every single day. Both of these model the inherent randomness because the type of person and the number of text messages they receive are both random variables. When we were coming up with this model, variables like lambda have been expressed in terms of lambda 1 and lambda 2, which have in turn been expressed in terms of alpha. And similarly, we have some tau, which is the place at which lambda 1 switches into lambda 2. However, these parameters, alpha and tau, so the parameter alpha cannot be further estimated as being dependent on some new parameter. The reason for this is because that we cannot reduce it down to a simpler process out of which alpha appears, and it is possible to measure the value of alpha by taking the number of text messages of all the different humans on Earth as samples, trying to fit them all with Poisson distributions, and trying to compute the parameters of those Poisson distributions as the exponential they are sampled from. So since this alpha represents the distribution over all people on Earth, we do not need to model this random variable further. We can just get the random variable from experiments, or we can take this to be a hyperparameter and see what values of alpha does this work well for. Next, the time tau at which the rate of messaging switches for our model can be assumed to be following a discrete uniform distribution from 1 to 70. Again, 70 is a hyperparameter. However, we know that for our model, on any random day the exam start or some other event happens, and therefore the switch point has to be somewhere in the middle, and since we have no information about where it is, we have a uniform distribution which is a completely uninformed prior. So the probability of the switch point being on any random given day k equals 1 over 70 because there are 70 different days this can happen on. We'll just plot the uniform distribution for completeness sake and take a look at how the sampling sort of makes it slightly jittery. And finally, given all of this, we have our Bayesian network with us, where we have this alpha, which is a hyperparameter, and it's is used to sample two different parameters, lambda 1 and lambda 2. These are both hidden, latent random variables, similar to the hidden layers in the neural network, which cannot be observed and which are not a part of our input, but they help us model the process better. And then using these lambda 1 and lambda 2 values, as well as this tau, which has in turn been sampled from some uniform distribution, we get the output parameter lambda, which is again a hidden variable, and using this lambda we can sample our final observations. So what we have done is, using our interpretation of probabilistic models, we have built this network which mimics the way we believe our text messages, like the number of text messages we send, work. This is a highly interpretable model because each of the parameters, lambda 1, lambda 2, lambda, tau, alpha, everything is interpretable. We know what it means, and if we end up figuring out what are the values of these parameters, we'll be able to comment on how much the increase was by, what are the percentages of the increases, at what point of time this increases, and so on. Therefore, Bayesian models are strictly more explainable than classical machine learning models, and in more ways than we have just experienced in the previous labs. So naive Bayes is not the limit of explainability of Bayesian models. Bayesian graphs are also very helpful in explaining. Finally, we need to put together some code which manages to solve this problem, and the code is reasonably involved. We have used TensorFlow probability to run this code. TensorFlow probability and PyMC3 are the two machine learning libraries which support Bayesian machine learning, and almost all code that is written would use one of these methods. The library and using these Bayesian techniques have been explained in the two links provided over here. However, it is absolutely not important for the reader to understand how the code is written. An appreciation of how Bayesian models work and why they are useful is sufficient for the purposes of this course. So here we would start by defining our parameters exactly the same way that we have. We define some alpha and sample lambda 1, lambda 2 with exponential from alpha, tau with a uniform probability distribution, and then we'll be sampling for every single day lambda 1 and lambda 2, and from that we would get lambda, which would be we'll get lambda I, which is dependent on tau. So we have lambda 1 and lambda 2s as initial guesses, and we are going to switch them, sample them for every single value I based on tau. So the first few elements would have lambda 1 as the parameter, and the last few elements would have lambda 2 as the parameter. And finally, xi would be the number of text messages that get sent, which we know as a supervision signal, and we sample that as a Poisson distribution over this generated lambda. Finally, we would need to represent the overall probability of our given the parameters and the parameters given the data that we already have. And since we have already talked about this in the previous lab, that taking products of probabilities is hard and computationally infeasible because everything falls off to zero because it's the product of a lot of small numbers. What we do instead is we take the log of all those numbers and add them together, because the product of numbers is equivalent to the sum of their log, and we never bring it back because it's monotonic in the log is monotonic in the value of its input. So here we have defined the product, and we define the probability of the posterior, the log posterior, and then we use the library TensorFlow probability to generate our samples. The sampling is done using the Hamiltonian Monte Carlo method, which is extension or a slight modification over the Markov chain Monte Carlo methods that we might have discussed in the previous lab. And the other method that can be used is expectation maximization. Again, both of these methods are beyond the scope of our coverage in this chapter over here. So we compute the samples from this Markov chain, and using the TensorFlow probability code. This TensorFlow probability code is easily searchable on their website and can be copy pasted as is after you have made the model. So the sampler code is not something that has to be written fresh for every single experiment. The the joint probability distribution is all that needs to be written for every experiment, and the rest of the code can be copy pasted from the TensorFlow probability guide. Finally, we get the acceptance rate and final step size, which are features of the Hamiltonian Monte Carlo process. We want there to be a reasonably high acceptance rate, which would mean that the number of samples that we generated, a large number of the samples were from the correct probability distribution, but we also do not want it to be too high of an acceptance rate, because otherwise something went wrong at the start, like the exploration part went wrong. So we want the acceptance rate to be reasonably high, and allowing it to fall below 50% would be a problem, because then we would not have drawn enough samples. Also, if the final step size would have been too large, then we might not have converged, and if it would have been too small, then we would have gotten stuck. 0.02 is a reasonable value of final step size, where we are reasonably confident that our model has converged to a nice sweet spot. All of this comes almost exclusively from experience and looking at other people's code on how they perform on these examples. Finally, we have these parameter value plots. So given this Markov chain Monte Carlo estimation process, we can compute the posterior probability distributions over lambda 1, lambda 2, tau, and so on. And what we observe is that lambda 1 is this is a smaller number of text messages. The Poisson parameter centered around a value of 18, and lambda 2 has a Poisson parameter centered around somewhere a value of 23. So we can take a look at what the distribution profiles for those would be. And finally, we have the expected day of the switch being on the day number 44, and probability of switch on day number 43 being slightly lower and other days being significantly lower. So something happened on day 44 which increased the average number of messages by a significant amount. And if we plot the data, what we notice is that the average number of messages from being somewhere around 18 went up to being somewhere around 23. And the value day number 44 was the switch point. And while it's not clear to the human eye that this is the true point of increase, we know from the ground truth data that this is the data from the author of the book that we have referred, going out of the city and having to text his moving to Toronto and having to text his girlfriend while it was Christmas. And this is correctly attributed on the 44th day. So it's amazing that things that the human eye cannot see at all actually match the ground truth effect that the person had, and it's well modeled by our Bayesian method. So that was all we have for the entire module. Thanks a lot for listening. I hope that you understand and appreciate how more complicated Bayesian models can be developed and how explainable and powerful they are, although they take a lot of compute to run, and therefore they cannot be scaled presently as well as deep neural networks. And I hope that you will be able to apply these to different problems in machine learning. Thanks a lot. Bye bye.